For this video, I want to talk about a SSD calculation to a depth and then normalized to an isodose line other than 100%. So a clinical scenario is a PA spine field where I have the skin surface, and then I'll have the spinal cord running along the posterior of the patient's body. I have my calculation point labeled CP, which is going to be at a 5 centimeter depth, and then I'll have my field size projected set to 100 centimeter SSD. Now the machine is calibrated to deliver 1 centigrade per monitor unit at 100 centimeter SSD, a depth of 1.5, which is D max for 6x, for a 10 by 10 field size. The physician wants to deliver 200 centigrade at the 100% isodose line at 100 centimeter SSD, 5 centimeter depth for a 10 by 10 centimeter field size. Now I know that for a PA spine field size we're not going to be using 10 by 10 clinically, however for this example it'll just make the math a little bit easy. I'm going to be using the beam data from the beam data tables in the course extras. I'll also have a link to the PDF available below this video in the soft chalk lecture. My monitor unit equation, dose divided by collimator scatter factor, phantom scatter factor, my depth component, which is going to be percent depth dose, and then my isodose line. I don't have to worry about inverse square factor in this example since I'm in a standard SSD of 100, which is where my machine was calibrated. For SSD calculations, you only need to worry about an inverse square factor if you use a non-standard SSD. Otherwise, the intensity, the decreased intensity caused by moving the calculation point deeper in the phantom, thus further from the source, is already taking account into the percent depth dose. I don't need a wedge factor, I don't need a tray factor. So I take mu equals 200 divided by my collimator scatter factor and phantom scatter factor located in the beam data table sheet for a 10 by 10 field size are 1.0 and 1.0 since that's how my machine is calibrated. My depth component, the percent depth dose, at the bottom I go across the top and look at equivalent square field size is 10, and then I go down to 5 centimeter depth, 85.8. My isodose line that I'm normalized to is 100. So my normalization factor is 1.0. Take 200 divided by 0.858, and I get 233 monitor units. So I need 233 monitor units to deliver 200 centigrade to this calc point, which is effectively at 100%. Now, that's where 100% of the dose is going. However, what if 100% of the dose doesn't cover my tumor or whatever the physician wants to use as a target? If my 95% isodose line covers the target adequately, the physician's going to say, I want to prescribe at the 95% isodose line. So then how are the monitor units adjusted in that case? So now the physician's changing his mind and he says, no, instead of 100% isodose line, I want it to go to 95% isodose line because I need increased target coverage based on the geometry that we've set. So my monitor unit equation changes. It says 200 centigrade. My collimator scatter factor and phantom scatter factor don't change. My depth component won't change. I'm still calculating to the same depth. However, my isodose line component now changes to 0.95. 200 divided by 0.858 times 0.95. 245. Does this make sense? The monitor units have increased. In fact, they've increased by about 5%. I've normalized down to the 95% isodose line, which means that I'm no longer delivering 200 centigrade to the calculation point. I'm delivering 200 centigrade to the 95% isodose line, which in effect is going to be deeper. I have left the machine turned on for a longer period of time in order to deliver 200 centigrade to a larger portion or a deeper portion within the patient. Now, because I'm normalized at the 95% isodose line, the dose at 5 centimeters isn't 200 centigrade. It's 200 centigrade divided by 0.95. So I'm delivering more dose at the calculation point in order to deliver more dose to the 95% isodose line. That's what normalization is.